This morning we welcome Dr. Amy Lowitz, who will be speaking on cosmology at the end of the Earth, studying the universe from the South Pole. Dr. Lowitz received her Bachelor of Science degree in physics from Brown University and her master's and doctoral degrees in physics from the University of Wisconsin-Madison. In 2016, she lived and worked for 11 months at the Amundsen-Scott South Pole Station, an NSF-operated research base located at the geographic South Pole in Antarctica. Currently a postdoctoral scholar at the University of Chicago Kavli Institute for Cosmological Physics, she works on instrumentation for the South Pole Telescope. So please join me in welcoming Dr. Amy Lowitz.
Thank you for that introduction, and thank you all for inviting me to speak here and for getting up at a reasonable hour on this Sunday, chilly Sunday morning. So I'm going to talk a little bit about the science that we do at the South Pole, why we go to all the trouble of building these huge instruments in such an unreasonable and remote location, and what sort of science, kind of an overview of the science that we do with these instruments. And then at the end, there's a little fun section where I'll talk a little bit about what it's like to actually live at the South Pole and what the station is like, what life is like at the South Pole. So, first of all, let's talk about what the South Pole is. It turns out there's 3 South Poles, and I'm only talking about one of them. So there's the geographic South Pole, and that's the one that I'm going to be talking about today, and that's the one that's right at the middle of the bottom of the Earth at 90 degrees south in latitude. So that's where the South Pole Station is, and when I talk about the South Pole during this talk, that's mostly what I mean. But there are 2 other South Poles. There's the magnetic South Pole, and there's the geomagnetic South Pole. So the magnetic South Pole is the place where the magnetic field lines, where the magnetic field of Earth goes straight down into the surface of the Earth. So this is an image from NASA showing you the rather complicated magnetic field of our planet Earth. And so the magnetic South Pole is the point where these lines go straight down into the Earth. And that moves around as Earth's magnetic field wobbles over time. And so in this graphic here from the World Data Center for Geomagnetism, you can see a little plot of where the magnetic South Pole has been over the years. So this is about 100 years of drift in the location of that pole. And so the predicted location in 2020, if you can't quite read the dates there, is out here in the Arctic, or the Antarctic Sea. So not a place that you can build anything or really go unless you're on an icebreaker boat. All of these are sort of just out in the middle of nowhere in the middle of ice, and there's not a lot of stuff there. The other one is the geomagnetic pole. So the geomagnetic pole is, if we took this really complicated actual map of where all of the field lines for Earth are, and we fit it to the closest matching simple dipole pattern, the place where those field lines go straight down into the Earth, that's the geomagnetic South Pole. And we've got a little plot of where that has been recently right there. So all of these are hundreds of miles apart, but the one we're talking about today is the geographic South Pole. So I'm going to talk a little bit about some of the science that we do at the South Pole Station. Just an overview. Unfortunately, there's not time to go too in-depth on anything, and I'm not going to talk about every single experiment. There are 4 major or flagship experiments at the South Pole, and I'll give you an overview of each one of those. But there are a lot of other smaller experiments. There are cameras that study the auroras during the polar night. There is an atmospheric observatory that has many small atmospheric monitoring experiments. That's run by the NOAA Corps. But I'll be talking about the 4 major telescopes that are at the South Pole. So the first one I'm going to talk about is the IceCube Neutrino Observatory. This is a neutrino telescope, though it doesn't look a lot like what you usually think of when you think of a telescope. And this experiment is headed up, it's an international experiment with many universities involved, but it's headed up actually right up the road at the University of Wisconsin-Madison. So there are a lot of people sort of right next door who work on this experiment. So this is a really interesting experiment, especially when you think of it as a telescope looking at radiation coming from space. First of all, it's huge. It's a kilometer wide, a kilometer deep, and a kilometer tall. So, of course, you might be thinking there are no buildings that big. Where would you put this thing? And you might have already figured it out if you're looking at my slide here. It's embedded in the ice at the South Pole. And so that sort of tells you right off the bat why this particular experiment is at the South Pole. There are not a lot of places on planet Earth where you have a kilometer of ice to bury things in. So that really narrows down your options. And you want really clean ice, ice that hasn't been disturbed, doesn't have, for example, dust from modern nuclear testing in it. And so again, the South Pole sort of wins that argument. And finally, you want a place that maybe already has some infrastructure, so you don't have to build up, say, your power plant and your dormitory housing and your cafeteria and all of that infrastructure from scratch. And it turns out there's been a station, a research base at the South Pole since the 1950s, and so it was a place where there was a lot of ice that was very clean and that already had some infrastructure in place. And so that's why we've gone to the trouble of building this huge thing all the way at the South Pole. So here's a graphic kind of demonstrating how large this thing is. First of all, in order to get down to the cleanest ice, the top of it is a kilometer below the surface. And it's a kilometer tall, so the bottom of it is 2 kilometers below the surface. And that leaves you with about 1/3 of a kilometer of leeway before you hit the bedrock. So there is, even though the whole surface of Antarctica is covered in ice, there is actually continental bedrock underneath. It is a continent with rock and bedrock and earth crust. It's not just a big blob of ice. So this sort of demonstrates that. This indicates the surface of the ice here where we can walk around and build buildings. And then these strands here indicate the strands of detectors that are embedded in the ice. Just to give you a sense of scale here, this little doodad is to scale with the Eiffel Tower. So this is how big the Eiffel Tower would be next to this experiment. It's very, very large. So I said it's a neutrino telescope. What is a neutrino and why do we care about them? So neutrinos are a fundamental particle. So fundamental particle, that means it's a type of particle that can't be divided into smaller particles. For example, an electron has no smaller parts. It's a fundamental particle. It can't be split into smaller things. Whereas a proton is not a fundamental particle. Even though it's very, very tiny, it actually can be divided into smaller things called quarks. So neutrinos, fundamental particle, can't be divided any smaller. We consider them a point particle. They don't have any dimension. They're in one point in space. And they're neutral. They have no plus charge or minus charge like a proton or an electron. So that gives them their name, neutral, neutrino, and that ending, ino, is an Italian ending for small because they are so small and indivisible. The other interesting thing about neutrinos is that they're incredibly, incredibly lightweight. So there are some particles that are massless, but among particles that are not massless, neutrinos are by far the lightest particle. In fact, they're so light that even though we know they have mass, we actually haven't figured out yet exactly how light they are because they're so tiny, they're really hard to weigh or to measure the mass of. But we know we have some limits on what kind of mass they might have. And so we know that they are less than 1/4 millionth the weight of an electron, which is already really tiny. So for a long time, we actually thought they were massless. We weren't able to measure their mass. But now we know that they do have some mass, and it's really, really, really small. So one of the things that this experiment might be able to do is actually help to measure that mass, or at least constrain some of the limits on what it might be. So neutrinos were theorized in the 1930s and first discovered in the 1950s. So it's a relatively new particle in the landscape of what we know about particle physics. And part of that is because they're really, really hard to detect. So right now, every second of every day, there are thousands of neutrinos streaming through your body. But you shouldn't worry. You're not being irradiated. Your DNA isn't being damaged like you would think of with a lot of other radiative particles. because they don't interact with anything hardly ever. It's very rare for them to have any kind of interaction with matter. Now, on the one hand, that's a good thing, because if there are that many streaming through you all the time, if they interacted with you, that'd be really bad. That'd probably mean that you wouldn't exist and there'd be no life on Earth or anywhere in the universe, because they would irradiate everything and damage any kind of biological thing trying to grow. On the other hand, it's a bad thing because it means that they're really hard to study. In order to study them, you have to be able to detect them. And in order to detect them, they have to interact somehow with some kind of detector. And so that you can see where the challenge there is. If they hardly ever interact with anything, it's really hard to build a detector for that. So that's why we build huge detectors, because if we want to have any chance of seeing anything with any kind of reasonable frequency, we need just a huge amount of volume to improve our chances to get the statistics that we need to study these things. And so that's one reason why we don't know a lot about neutrinos. We don't know as much as some other kinds of particles about the ways they interact on large time scales, large distance scales, at high energy scales. They're difficult to study. So that's the motivation for building a huge telescope like this. So what sorts of things are we studying with this thing? Well, it's made up of a bunch of what we call digital optical modules, or DOMs. They're about this big, they're spherical. There's actually a spare one in the Space Visualization Laboratory at Adler Planetarium. So if you want to see one in the flesh, stop by the SVL at Adler and check it out. There's also a light-up LED model of this experiment there that's really cool. So there are these digital optical modules, and they're what we call a photomultiplier tube, which is just a super sensitive light detector. So sensitive that it can detect single photons. And so what this detector, this kilometer cubed detector, is made of is strands of 86 of these DOMs, these photomultiplier tubes, and on each strand, or sorry, there's 60 DOMs on each strand and 86 strands to make up the whole cubic kilometer. So that's 5,160 photomultiplier tubes, or individual sub-detectors making up the whole cubic kilometer detector. Incidentally, if it wasn't clear, that's where the name of the experiment comes from. It's a cube in the IceCube. We're not that creative with naming in physics land, it turns out. Also, not to be confused with the musician IceCube. That guy has a space. This has no space. So this instrument is hoping to detect high energy events in the cosmos. So really high energy astrophysical events produce, among other things, bursts of high energy neutrinos. And the cool thing about this experiment, because it's made up of a bunch of individual sub-detectors, these DOMs, you can have time resolution for where you see an interaction first. So you'll know if this one sees it first, or this one, or this one, or this one, or this one, and you'll see what order they all see an interaction in. And so that means you can backtrack and see what direction these high-energy neutrinos came from, and you can potentially localize them on the sky and figure out where they came from, maybe even specifically what astrophysical object they came from. That happened for the first time last year. They were able to localize to a specific object, a blazar, which is a type of active galactic nucleus that has these jets, these super high energy relativistic jets that point out of them and spit out super energetic particles. And it happens that that jet is pointed right at us. And so we can see it really brightly. So that was the first time that they were able to localize to a specific object instead of just kind of a direction in the sky. So that was really exciting. Even with this huge detector, we only see a handful of events per year. So that's why you need this huge, huge thing, because even with this huge, huge thing, you're not seeing that much. But when you're seeing something, it's a really high energy event, and it's really interesting, and hopefully we can localize it and figure out where it is. So that's the IceCube Neutrino Observatory, and that is one of the 4 kind of flagship experiments at the South Pole. This picture here is the above ground part of the experiment. So this is actually the only part of the experiment that you can see because all of the strands of detectors are under the ice, under the snow, where you can't see them anymore. So this building, basically all of the wiring from all of those detectors comes up through these silos on each side and goes over the bridges into the building. And then the building just contains a bunch of computer servers that record all of the data and do sort of initial data cuts to cut out all of the boring, nothing is happening data and select the data where something might be happening for people to go through and look at it in more detail. So this is an artist's impression of what the DOMs look like. So each one of these things, like I said, is about this big. And then they're on these strands drilled into the ice and then filled back up with water so that they're frozen in and embedded in the ice. All right, so that's one of the four. Now let's talk about the other three. And I'm going to talk about the other three kind of as a group because they're very similar. So there are three major microwave telescopes at the South Pole. So these telescopes are studying something called the cosmic microwave background, and I'll talk a little bit about what that is in a moment here. In this picture, you can see two of them. So this is the South Pole telescope, which is the one that I work on. And then at the other end of the same building, right here, you can see the BICEP 3 telescope. And then there's another one just down the road, just out of frame, kind of over here, called the Keck Array. That's the third of these microwave telescopes. So this is a view of the night sky. It maybe looks a little bit familiar, though there aren't too many places in the world where you can see the Milky Way quite that well. This is another view of the same night sky, zoomed out a little bit. So this is a computer simulation of all of the large-scale structure in our universe. So this gives you kind of a distance scale here, 125 megaparsecs per h. So that's a big distance if you're not familiar with those limits. That's huge. So each one of these little points of light is an entire galaxy, to again give you a sense of the scale of this image. And so this shows the largest structures that exist in our universe. Galaxy clusters, which are these nodes. And then we also have these kind of filamentary structures that form in between the nodes. So this is what our universe looks like. Sometimes people call this the cosmic web or the cosmic foam. And so how do we get here? Well, it turns out the very early universe is seeded by just random fluctuations. Everything is almost completely even and dense and hot, but they're just random quantum fluctuations. One spot's a little more dense, one spot's a little less dense, and that the more dense spots have a little more gravity, and so they glom on a little more stuff, and then a little more stuff because they have a little more gravity, and that continues over billions of years and gives us this structure. So the cosmic microwave background is sort of where that all begins. So this is another view of the same night sky. This is a picture of the cosmic microwave background. So this is what you would see looking at the night sky if your eyes could see microwaves instead of visible light. So now let's talk a little bit more detail about what the cosmic microwave background is. So first of all, it's cosmic. That means it's the whole universe. It pervades the entire universe, certainly the visible universe, probably even the unobservable universe that's so far away we can't see it. But we'll never know because it's so far away we won't ever be able to see it. So that's what we mean by cosmic. It's everywhere. Microwave, so that's a wavelength of light. It's not a wavelength of light that we can see, but it's still made of the same stuff that comes out of the sun or that comes out of the ceiling lights. It's still made of photons. Those photons just have a different wavelength or a different frequency that our eyes don't happen to be sensitive to. So this is kind of a demonstration or a little graphic of what the electromagnetic spectrum looks like. So the visible part of the spectrum is just a tiny slice right here that your eyes can see, but there's all of these other wavelengths that we can make cameras that can detect these wavelengths, even though our eyes can't see them. So we're talking about microwaves at these particular wavelengths. We're talking about sort of centimeters to millimeters of wavelength, whereas visible light has a much shorter wavelength. And background. So background can mean kind of two different things in English, and we're actually kind of using both meanings. So one meaning of background is something that's sort of behind other things that are in the foreground. So in this case, the cosmic microwave background, we see it behind all the foreground stuff, which is the galaxies and galaxy clusters and stars and planets and all of that kind of thing that formed at more recent times that are closer to us in space. But it's also a background in the sense that you might call something like a background noise. That's something you're not paying as much attention to, but that sort of pervades a space. So the cosmic microwave background is everywhere. On average in the universe, every cubic centimeter of space has about 400 cosmic microwave background photons in it. So this is radiation, low energy light that pervades the entire universe. So it's a background in that sense as well. Okay, so I told you what cosmic microwave and background are, but for real, what is it? That's not a very helpful definition. So this is my artistic impression of what the very early universe looked like. So in the beginning, everything right after the Big Bang, everything is really, really hot and really, really dense. And in particular, it's so hot that electrons, minus charges, can't stick to protons, plus charges, because, so one electron and one proton is neutral hydrogen normally. But it's so hot and there's so much energy that even if they start to try to stick together, there'll be some really energetic particle that whizzes past and hits them and breaks them back apart. So they can't stick together. Even if they kind of try to start to, they'll get ripped apart almost immediately because it's so hot and so energetic in these first moments of the universe. And so what that means is that everything is what we call ionized. The pluses and the minuses can't stick together. They're all running around separate. So we have all these negative electrons running around separate from all these positive protons, and we've also got a bunch of photons running around in the mix as well. So why does that matter? Well, it turns out that photons really like to scatter off of ions, any plus or minus charge running around by itself. And so in this early universe, the photons, the light, is scattering pretty much all the time. So a light, because everything's really dense, a particle of light, a photon, can't travel very far before it hits an ion and bounces off and changes direction. So that means the light from this early time is getting scrambled constantly. It's kind of like a dense fog, this early universe. So just like in a really dense fog, you can't see through it because the light's getting scattered off of all of the tiny particles of water that are in the air. In the early universe, it's like a dense fog. You can't see through it because the light's getting scattered and scrambled by all of these ions running around everywhere. So we can't see through this early universe. It's opaque. But as the universe continues to expand and cool, eventually, about 380,000 years after the Big Bang, it's expanded just enough and cooled off just enough that those electrons finally can stick to those protons, and their binding energy is enough to keep them together despite the heat surrounding them. And so now, all of a sudden, very quickly, at least on universe scales, the universe goes from almost completely ionized to almost completely neutral, and almost all of the electrons and protons buddy up into neutral hydrogen. And this happens quite rapidly. And so all of a sudden, those photons don't have anything to scatter off of anymore. And so they pretty much travel in a straight line for the next 13.8 billion years until today. There's essentially nothing left for them to scatter off of, or at least they don't scatter very much. So most of the photons in the universe have been traveling in an essentially straight line for 13.8 billion years until they hit the detectors in our telescopes, and we capture them and we measure them. So what that does for us is we're basically taking a picture of that last chance they had to scatter before everything became neutral. We're taking a picture of that wall of fog in the distant past. And so that's what we're looking at when we look at this view of the microwave sky. So the microwave sky is almost exactly even in every direction. So it's almost exactly 2.725 Kelvin, degrees above absolute zero, in every direction, that way, that way, that way, that way, that way, that way, all the ways. But there are tiny, tiny variations on that almost smooth temperature. 1 part in 100,000, and that's what all these lumps and bumps that we're showing here are. We've subtracted off the average from this picture, and we're just showing you the lumps and bumps, the 1 part in 100,000 blown up with these colors. So the hottest spots and the coldest spots are 1 part in 100,000. And these hot spots and cold spots come just from those random fluctuations that I talked about. Spots that are slightly denser and hotter, spots that are slightly less dense and cooler, that eventually gravitationally sort of glom on more and more stuff and make all these large-scale structures that I showed you a few moments ago. So that's what the cosmic microwave background is. So we have these 3 telescopes at the South Pole with microwave detectors in them. Why have we put them at the South Pole? It was pretty obvious why we put IceCube at the South Pole, because we needed a whole bunch of really clean ice and some infrastructure. Why are these things at the South Pole? There are lots of other places with infrastructure that supports telescopes in reasonable places like Hawaii and the American Southwest and lots of places in Europe and, you know, maybe places that more people would like to visit than the South Pole, though I happen to really like visiting the South Pole. So why do we put these at the South Pole? Well, it turns out that water vapor absorbs microwaves. And this is the fundamental reason why your kitchen microwave works, incidentally. So the way your kitchen microwave works is it spits out microwaves. It has a thing that produces microwave radiation inside it. And it sprays that radiation at your food. And the water in your food absorbs that energy and heats up. So microwaves, for example, don't work very well if you put something with no water in them. If you try to microwave a saltine cracker, it's not going to heat up. And that's why, because there's no water in it, and the whole way that a microwave works is by putting energy or heat into water. So that's a problem for us with microwave telescopes, because if there's water vapor in the atmosphere that we have to look through to see space, then that water vapor is going to basically absorb and steal from us all of our photons that we're trying to collect, and we won't be able to see anything, or we won't be able to see as much. And so we want to be somewhere incredibly dry. The other thing we want is to be somewhere that's at high elevation, so that on top of being somewhere dry, we're also just above a lot of the atmosphere. So we have even less water vapor between us and space. And so it turns out that there are really 2 sites that are good for this. The other thing that you need, incidentally, is a place that's accessible and has a stable government. So that actually does rule out a couple of locations. There are some good locations, for example, in parts of Africa that don't have the stable governments we need. Also areas like Tibet that aren't stable for putting telescopes in. There are also some places that are less accessible, believe it or not, than the South Pole. For example, in the middle of nowhere in Australia, that would be okay for these types of telescopes, but because they're so inaccessible, we don't put telescopes there. The 2 places we put these kinds of microwave telescopes, besides in orbit, which is the best, but also really expensive, the 2 places on Earth that we put these things are in the Atacama Desert in Chile, on the mountains that are in that desert. So that's an incredibly dry desert, even drier than the Sahara. The Sahara is actually not that dry a desert, even though a lot of people think of it as the quintessential deserty place. It's a desert for sure, but it's not like super deserty. So the Atacama Desert in Chile is much drier, and it has some really nice tall mountains, so you can get above a lot of the atmosphere on top of that. And then the other place, the driest desert on Earth, is the interior of Antarctica. So not specifically the South Pole, kind of anywhere away from the coast is fine, but there happens to be a bunch of infrastructure at the South Pole, and so that's the place that we picked. So this is actually the best site on Earth for microwave telescopes. It is the driest atmosphere, so even though the ground is all water, it's frozen, and we don't care about water under the telescope. We only care about water over the telescope, and it happens that there's basically none. So that's why we go to the trouble of putting these telescopes all the way at the South Pole. Turns out there's actually pretty good infrastructure there with the research base that's been established for 60 years. And we have very little water vapor, so we get really great images of the sky, really a lot of the photons coming from the cosmic microwave background make it all the way through our atmosphere to our telescope. So that's the motivation. That's why we go to the trouble of building these things all the way at the South Pole. So a little history of the microwave telescopes at the South Pole. Like I said, there are 3: BICEP, Keck, and the South Pole Telescope. So the original version of BICEP was running from 2006 to 2008, and the current version of BICEP, which is the 3rd camera, creatively called BICEP 3, has been running since 2015 and is running right now as we speak. The Keck Array is another microwave telescope. That's the one that you couldn't see in that picture of 2 that I showed a little while ago. You'll see it in a picture in a minute here. So the Keck Array is actually the same collaboration as the BICEP collaboration. It's one collaboration with 2 telescopes. And that has been running since 2010 and is still running today. This is actually its last year of operation. It'll be decommissioned in the upcoming austral summer, so our winter, their summer. And then it will be replaced with a new telescope called BICEP Array, not to be confused with BICEP, which will still be running. So their naming situation's getting a little confusing, but it's okay. And then the third is the South Pole Telescope, which is the one that's pictured here and the one that I work on. And that one has been, the original camera on this telescope was commissioned in 2007. So we're now at over a decade, which is pretty exciting. And the current version of the camera, which is the 3rd generation camera, creatively named SPT-3G, was just commissioned in 2017. So we've been running now for 2 years with that telescope, or with that camera on the decade-old telescope, which is pretty exciting. So now we get to the kind of even more fun part of the presentation. I'm going to talk a little bit about what it's actually like to live and work at the South Pole. What's the station like? What is it like to be there? How do you get there? So this, incidentally, is the picture that I have that actually shows all 3 of the microwave telescopes. So there's the South Pole Telescope, there's BICEP 3, and there's Keck Array in another building just down the road. And this picture is taken from the main station to give you a sense of kind of, that's my morning commute when I'm there. The traffic is terrible. And you can actually see, so this is a photo of the last LC-130 departing in my winter. So everybody goes outside to see it off. And they do a little flyover of the telescopes as a little goodbye. All right, so we already talked about where we are. We're right in the middle here. It turns out Antarctica has a whole lot of other stations. So a lot of countries have their own bases in Antarctica. The US has 3 permanent bases that operate year-round, in addition to many field camps that operate only in the summer. So we have the South Pole Station, which is where I was. We also have McMurdo Station down here on Ross Island. That's the largest station, and that sort of provides logistical support to the South Pole Station and to most of the US field camps. And then finally, out on the peninsula, we have Palmer Station, which is accessible only by boat. So you leave from southern Chile to get there and cross the Drake Passage for 4 days on a boat. And as you can see, there are lots and lots of other stations. Some of these operate year-round. Some of these are summer only. Our nearest neighbors are a Chinese station that's summer only, and then a year-round Russian base called Vostok. So those are our nearest neighbors at about 800 miles away. So it's a long walk if you need to borrow a cup of sugar. Little history. So the South Pole was first accessed by Roald Amundsen on the 14th of December, 1911, followed by Robert Scott on the 17th of January, 1912, so just over a month later. The story many of us know, Roald and his team made it back in one piece and were revered for the rest of their careers. Unfortunately, even though Robert Scott and his team did make it to the South Pole, they did not make it back. They perished from exposure and insufficient food, essentially. They were about 3/4 of the way back, so they very nearly made it, and they were in fact only a few kilometers from their next cache of supplies, but they were lost and didn't realize how close they were. So it's a bit of a tragic story. There are lots of interesting books that you can read about that, including some of the men's own diaries, if you're interested in learning more about that adventure. So this is the Amundsen team at the South Pole, a photograph that they took while they were there. So the South Pole has been continuously occupied since the 1950s. The first flight to the South Pole was on the 20th of November 1956. 2 R-4D airplanes landed and dropped off men and supplies. A bunch of additional supplies were airdropped, and then they built a station, which we call Old Pole. So these are some old aerial photographs of the station. I know they're a little bit hard to see even when you can see them up close, but this is sort of the main building, and then there's a communications building out here and a bunch of other kind of outbuildings and support buildings off to the side. So again, this was built in 1956, and it's been continuously occupied ever since then. So those men who were dropped off by those 2 airplanes stayed for the winter. And then more men were brought in the following summer, and it's been a US base ever since. In the 50s, it was a Navy base, though now it is fully civilian, operated by the National Science Foundation. So following Old Pole, when that station was getting too old and too covered with snow, they built the dome in 1975. So that station was a geodesic dome, 50 meters wide and 16 meters tall, unheated, but then there were heated smaller buildings built inside the dome. So the dome was basically keeping snow from building up around the buildings and blocking the wind, and then you had smaller sort of shipping container buildings inside that people lived and worked in. The dome was decommissioned in the early 2000s, and the new station, the elevated station, which is what you see here, was the first planning for it began in the early 90s, actually. Construction began in 1999, and it was dedicated on January 12th, 2008. So we're actually at slightly over a decade on the what we still call the new station today. So in that station is housing. So we use a lot of the old sort of nautical terminology still, even though it's not a Navy base anymore. So we don't call them dorm rooms, we call them berthing rooms. We don't call it a cafeteria, we call it a galley. So that's where the berthing rooms are, a bunch of dorm rooms for all of the scientists and support staff living there. A galley with galley staff, so people who are cooking for the whole station. There's also some office space, some recreational space, a gym, some lab space, and then most of the big experiments are actually in outbuildings. So this gives you kind of an overview of the site as it is today, or at least recently. So this is the main station right here, this little blob that's a little bit hard to see. This is IceCube. This is Keck Array, and this building here is South Pole Telescope and Bicep. So that kind of gives you the lay of the land. So the atmospheric observatory is out here. And then all of this stuff is all of the kind of logistics and operational stuff. So anything that can be kept in cold storage outside. There's rows and rows of crates out here to store all of the cold supplies. All of the cargo operations happen out here, and all of that kind of logistical operational stuff. The airstrip is right here. So we have a skiway where planes can land. The main access is with LC-130s, which are military cargo planes. In particular, we have the New York Air National Guard supporting the South Pole. So they have LC-130s, which are just like C-130s, except they have skis, so they can land on snow. And we're also supported by Baslers and Twin Otter planes, which are smaller planes that can land even on ungroomed snow. A little bit about station life. So this is one of those New York Air National Guard LC-130s. How do you get to the South Pole? Well, you fly commercial to Christchurch. So it's quite a coincidence that we happen to be having a talk that deals with Christchurch and the South Pole on this particular week, given the tragic events that happened there recently. So Christchurch is near and dear to the hearts of everybody who works with the U.S. Antarctic program. They've always been incredibly welcoming to us, and everybody involved in the program has spent a lot of wonderful time in Christchurch preparing to go to the ice and leaving the ice. So you fly commercial to Christchurch, you spend your first day in Christchurch, you go to the Clothing Distribution Center, the CDC, where they give you all of the warm gear that you need to be at the South Pole. So you don't have to know how warm a coat you're going to need. They make sure that you have all the right stuff. And that's partly because a lot of this gear is incredibly expensive, and so it makes sense to sort of buy it en masse and lend it to people. And also because they don't want somebody who goes there under-equipped to become a burden on the station and pose a safety risk to themselves and to other people. So they give you all the super warm stuff you need, the giant coat, the insulated pants, all kinds of gloves and mittens and boots and everything that you need to get by in the polar summer or the polar winter if you're wintering over. So this is all of the stuff that I brought with me to the South Pole when I wintered over. So most of it is cold weather gear. So this suitcase here and this little duffel bag were my personal things for 11 months at the South Pole. And all the rest of that stuff is cold weather gear. Just to give you a sense of the voluminousness of the gear. And there's me all geared up for going outside in the winter. So that's what you look like when you're going outside when it's minus 70 out. Temperatures, so one common question is how cold does it get? In the winter, the coldest temperatures that I saw were minus 105 Fahrenheit with a minus 150 wind chill. And I did go outside in that, just to be clear. We have to walk out to the telescope every single day. So you go outside, if you're working on the telescope, you go outside every day and you walk out there and take care of the instrument. But you're dressed really warm, so it's okay. It's not that bad. In the summer, temperatures will occasionally break 0 Fahrenheit if it's really nice out. So the next thing after Christchurch is you fly on either a C-17 or an LC-130 to McMurdo, which is the largest base. It sort of looks like an Alaskan mining town, kind of. And there is some biology that happens there, but it's mostly an operations center. So it's mostly supporting the South Pole Station and all of the field camps. So there aren't a lot of scientists there. It's a lot of support staff. And then you take an LC-130 to the South Pole. So this is the pole marker from 2016. It gets changed every year. And this is a view from the other side of the station, so you can see the telescopes kind of off in the distance there. We have a galley, or a cafeteria. So this is where everybody gathers 3 times a day to eat. There's a kitchen area back there, and this is where everybody sits together for meals. We also have Sunday science talks in the galley. This is what a typical dorm room or berthing room at the South Pole looks like. So one of the great advantages of the South Pole is everybody gets their own room, which is not the case at McMurdo. So that's a huge advantage. It's small. All of these photos were taken with a really wide-angle lens, so all of these rooms look a lot bigger than they are. It's small, but it's your own space, which is really, really nice. So it's, dorm furniture, a dorm-style bed, a small desk. There's a wardrobe off to the side that you can't quite see, and that's your space, shared dorm-style bathrooms and showers. There's also some recreational space. So everybody at Pole works a lot of hours, very hard, but that means it's important to also be able to decompress and enjoy the time when you are off work. So we have a game room with a bunch of board games and a pool table and a small library of books here, and then a movie screening room. There's actually 2 of those with some couches and a big screen for people to watch movies. There's a DVD library. Since we don't have very good internet, and the internet we do have is only up for a few hours a day, there's no Netflix, no iTunes, no Pandora streaming music. Everything is hard copies only. So there's a large DVD library with TV shows and movies so that you can still entertain yourself when you're off work. There's also a gymnasium. So people play, there's a volleyball net that people put up in here, or people play basketball or tennis, or sometimes someone will volunteer to run yoga classes, and those take place in this space here. There's also like a cardio and weight gym for people to stay in shape while they're at the South Pole. We have a music room and a craft room, again, for people to enjoy their time when they are off work. We also have a library and a quiet reading space. So that's what this is. And we have a tiny greenhouse. So the Antarctic Treaty forbids bringing any kind of soil to Antarctica in order to preserve the flora and fauna, particularly on the coast. And so you're not allowed to have soil, so our greenhouse is fully hydroponic. And so we grow a small amount of stuff to eat. Even in the summer when there are regular flights, we don't get a lot of fresh fruits and veggies in because a lot of the weight allowance of those flights is taken up by equipment for doing science. So we do get a few shipments of fresh fruits and vegetables in the summer, but most of the fresh fruits and vegetables in the summer and all of the fresh fruits and vegetables in the winter come from this greenhouse. So if it's a good year and the people who are volunteering to run it are doing a really good job, there might be enough for 2 or 3 salads for the station each week through the winter. So that's not too bad, actually. They try to focus on stuff that grows pretty fast to kind of keep up the morale from the nice greens. We also have kind of a regular laundry room like you might see in a large apartment building. You're allowed one. So water is very expensive to melt. Costs a lot of fuel to melt water. So even though we're sitting on a whole bunch of water, it's very expensive to melt it. So we are on water restrictions year-round. You get 1 load of laundry per week, and you get 4 minutes of shower per week, which you are free to divide up however you please. The recommendation is 2 2-minute showers per week. But keep in mind, it's really dry, so sweat evaporates really fast before it can grow too much bacteria and make you too stinky. And also, your mucous membranes are really dry and you can't smell anything. So actually, nobody's stinky. Or you can't tell. So with that, I would love to take any questions. Thank you very much for your attention.
Over here.
How long of a period of time are you there for? Are you there in shifts or just ones?
So it depends on what you sign up for. So if you sign up to winter, the absolute minimum is 8.5 months. That's the amount of time in the winter when there are no planes in or out or vehicles of any kind. So you're stuck if you sign up to winter. So for my winter, I was there for 11 months. So there was a few extra weeks at the beginning to be trained, and then a couple weeks at the end to do turnover. In the summer, for our experiment, typically we do kind of 2 shifts. So the beginning of the season, people will be there for 2 to 2.5 months, and the end of season people will be there for 2 to 2.5 months and switch over in the middle. But in principle, depending on what job you're doing, you may be there for the full 3.5 months of the summer, or you may be there for a shorter time, depending on your role.
Yes, thank you for your fascinating presentation. A question I had, though, can you comment a bit on how you design these experiments? Absolutely fascinating. How you engineer them, and then how you build them in this climate.
Yeah, so I mean, that's a huge question. You could do an entire talk or even a series on that. But things that you have to consider. So the detectors that we use are superconducting detectors, and superconductors only superconduct at very low temperatures. So our camera is cooled down to 1/4 degree Kelvin, or 1/4 degree above absolute zero. So that's one important design consideration, is that you have to be able to cool things down that cold. So that requires a cryostat and a pressure vessel, and that's a lot of weight, and so you have to have a telescope that has an appropriate structure and appropriate counterbalance to support all of that weight. Another thing to consider is pointing, so you have to be able to control the telescope and know exactly where it's pointing and figure out how you're going to measure where it's pointing. Another issue is optics, so how are you going to make lenses? For the South Pole telescope, which is the one I know the most about since it's the one I work on, our lenses are 700 millimeters across, so they're about like this. That's a really big lens. So smaller telescopes in the millimeter wave range, so glass lenses do us no good in the microwave range. So in smaller telescopes in the millimeter wave range, they use silicon lenses. But silicon crystals are only available up to about 40 centimeters, and we need 70 centimeters for our lenses, so we have to use a composite ceramic material called alumina. And so then that means you have to think about where you're going to source this, how are you going to machine it into a lens shape. You have to make anti-reflective coatings for these lenses, just like there might be anti-reflective coatings on your glasses or on your regular home consumer camera lenses. But of course, those AR coatings don't work in the microwave, and so you have to make your own. So you also have to consider snow accumulation. How are you going to remove the snow that builds up, for example, in the telescope boom? You have to have human access to all of the different parts of the telescope, even in the winter, to be able to maintain everything. So that's part of why the bottom part of our telescope is embedded in a building. So you can actually access a lot of the mechanics of the telescope from a heated space. Not all of them. Some maintenance work you do have to go outside and work outside. So those are some of the considerations when you're designing these types of telescopes.
Thank you, fascinating. 2 questions. One is, as a humanist trying to help humanity, help the Earth, help all others, how does this fit into that, if it does? And then how do you create the energy and the backup to keep all this going?
So, I think there's two answers to why is this kind of science worth doing that are directed maybe at 2 different kinds of people with some overlap. So there's first, we're taking baby pictures of the universe. We're learning about how the universe worked in the first moments after the Big Bang. And I think a lot of people would consider such a fundamental question about how the universe that we have sprung forth from works to be sort of on its surface worth doing just from that. But that obviously doesn't convince everyone. Not everybody is interested in spending tax dollars on something that isn't going to really directly benefit their life right now. And so I think the answer to that concern, obviously I am a ward of the state. I am paid entirely by tax dollars by the National Science Foundation. And so that is something that I think about a lot. But one thing that I think really helps justify a lot of that pure science spending is actually that's the highest return on investment of anything that the US government spends money on. And so the thing about pure science research is you don't know which thing is going to hit big, because if you already knew that, it would be engineering, not pure science, and it wouldn't be a very big risk, which means it's not going to be a very big return. But so you don't know which project that you're funding is going to hit big, but when they hit big, some of these things really completely change the world. So the transistor was invented out of a pure science project. It wasn't motivated by, oh, we're going to make a thing that'll make a radio and then make computers and cell phones and change the world. They were just messing around with electronics and seeing what they could make. MRIs were, again, somebody just being like, well, let's play around with magnetic resonance and see what we can make. And then it revolutionized the way that we do medicine. The internet was a pure science project in figuring out how networks work, just from a purely academic perspective. And then people realized it was incredibly useful. And so these are just off the top of my head 3 examples where pure science research has completely changed the entire landscape of the economy and generated more money than you could ever imagine. And so that is what makes pure science funding the highest return on investment that we spend our tax dollars on, and it's what makes it worth doing in a way that benefits every single person directly. So will any of the technology that we're doing here be one of those hit big things? Who knows? Probably not. Most science projects don't hit big, and they're just the feel-good, let's learn about the universe stuff. But you never know which one it's going to be, and so that's what justifies it.
And the energy?
The energy. So people have looked into doing wind power. Obviously, you can't do solar at the South Pole because it's dark for 6 months a year, straight, continuously. So we have, in case that wasn't clear, we have 1 6-month day and 1 6-month night because we're at the very end of the Earth. So no solar. One of the concerns is because we're so remote, you really have to have stuff that you can maintain and that you can hire people who can definitely fix it. And so that is something that has kept us on fossil fuels. So we're run off diesel and AN8 with a standard traditional generator array. So we're not very carbon neutral. It's pretty bad, but people have looked into other options, but right now it's not safe to try to implement less well understood systems.
With the length of time that you have to spend in such isolation, do you have any medical staff available, and how are people cared for if they have a really serious emergency, health-wise or an accident?
Yeah, so that's a great question. There was not a picture of the medical suite in the station tour because there was a patient in there when I was going around taking the pictures for the photo tour. So we do have year-round medical staff. We have one doctor and one physician assistant or nurse year-round all the time. So that means if one of them gets sick, there's still somebody else who can take care of them. There used to be only a doctor and no PA or nurse, and then the doctor was the person who got sick a couple of times, and then they started hiring 2 people. So yeah, we have actually a pretty impressive medical suite considering that we're at the South Pole. There's a full dental suite. There's a digital X-ray machine. There's a ultrasound machine. There's surgical supplies should that be necessary. There's a whole suite of blood testing equipment, so we can do all the kinds of blood labs that you might expect in any kind of real-world clinic setting. So there are a lot of ailments that we can take care of at the South Pole. There are also obviously a lot that we can't. We're not a level 1 trauma center by any stretch of the imagination. So there have been, I said there's no access for 8.5 months. That was a little bit of a fib. If somebody is extremely ill and falls into this so it's incredibly risky to fly to the South Pole in the winter, but it can be done. The Twin Otter planes can land and take off with some modifications even in the winter. So that has been done 3 times, including in my winter. We actually had a midwinter, so right in the middle, double medevac. There were 2 patients who coincidentally became ill in completely unrelated situations within a week of each other. And they were both evacuated on a single Twin Otter. So the situation in which you would evacuate somebody because it is so risky for the people bringing the plane to you and taking you back out, it's sort of a very narrow window. It needs to, this is a little bit morbid, but you need to be in that window where if they got you out, you will very likely live, but you can survive for the 2 weeks it will take to get a plane there. So it takes a minimum of 2 weeks to get a plane to the South Pole after somebody is determined to be ill enough to need one. So there are only a limited number of things where you can make it the 2 weeks and then be okay if they get you out after that. But in those situations where you're sort of very likely to die if they don't come get you, but you can make it 2 weeks and then you'll be okay if they do come get you. It has happened 3 times and they do it. So that's the recourse if something comes up that they can't handle with the resources at hand.
Hi, thank you. What are some of the outstanding or top science questions that microwave astronomy hopes to answer with a new bicep array? And then the second question is, has climate change impacted operations at all, specifically with the IceCube operation?
So I'm going to answer the second question first. So climate change is obviously, we have a climate observatory at the South Pole, and so it's something that, I think everybody in the science community thinks about a lot, and especially when you've got a whole observatory right there with some of the world experts on climate and measuring climate. The South Pole's a little bit unique because of the way the wind patterns are in Antarctica. We're actually a little bit more isolated from some of the big climate changes that they're seeing in the coastal regions. So we don't see as much difference in, say, annual average temperatures as other parts of Antarctica see, and certainly other parts of the globe, just because of that kind of unique wind pattern. But we have seen, and the weather at the South Pole tends to be fairly, we don't get real proper storms. Things get kind of cloudy and windy, but it's not like on the coast where you get these incredible storms where nobody's allowed to go outside because it's too dangerous. And that's partly because it's so cold at the South Pole, there's not that much energy in the weather system to drive storms. And because we don't have any day-night cycle, and we're so far away from anywhere that has that day-night cycle, we don't have that changing temperature from day to day that drives winds and currents and things like that to drive storms. That said, it has actually been a big problem with increased poor weather in McMurdo. It's been more difficult to get enough flights in. So the weather needs to be good in McMurdo in order to get a flight from McMurdo to Pole and back. And they have to be able to make the full trip in one day. They can't leave planes at Pole because the fuel gels up and they can't take the plane back off again. So they have to have a large window of good weather to get a flight to Pole and back. And the changing weather and the increased rate of storms in McMurdo has been a problem for keeping Pole supplied. So that's one way in which operations have been very much impacted at Pole by climate change related issues. I forgot what your first question was.
The top science question.
Yes. So that's a really broad question because we can actually do a lot of different stuff with these microwave telescopes. So the kind of holy grail thing that all of these microwave telescopes are going after is something called inflation or cosmic inflation. So you might be aware that the universe is expanding and that it's accelerating in its rate of expansion. But that's not exactly what we mean by inflation. This is one of those science words that means something very specific and different from what it means in regular people speak. So inflation refers to a moment in the first second after the Big Bang. So the Big Bang happens and the universe is expanding, and inflation is this moment of super fast exponential expansion that turns on and turns back off, and we don't know exactly what turns it on and turns it back off. But we see this moment about 10 to the minus 34 fraction of a second after the Big Bang, and of duration about the same, about 10 to the minus 34 fraction of a second in duration, where the universe expands by many orders of magnitude in size in that tiny moment. And this resolves several paradoxes that we don't have other resolutions for. Like, this is the only idea that anybody's come up with that sort of solves these paradoxes and doesn't create more problems. And this moment of inflation would leave a certain imprint on the cosmic microwave background that's very, very faint, even fainter than those temperature fluctuations I showed, by 2 to 3 orders of magnitude more faint. And so that's what we're all looking for now, is that particular imprint that if that happened, we would be able to see in the cosmic microwave background today. But it's very faint, so it's very hard to detect. So we're building bigger and bigger and bigger telescopes that are more and more and more sensitive to try to see it. So that's kind of the holy grail thing that we're all going after, is to figure out, okay, did this thing happen? Or if not, we don't have any other good idea to explain away these problems. So we really need to go back to the drawing board and go looking for new physics to try to figure it out. But other things that we can do with the cosmic microwave background, the reason the South Pole Telescope has this huge dish, which you saw, or you can see now in that picture kind of, or that you saw in some of the other pictures I showed. It's a 10-meter dish. The bigger your dish, the finer your angular resolution on the sky. So we actually have the ability to resolve galaxies and galaxy clusters. And so we can do things like study lensing of galaxies, which helps us map out where all the stuff in the universe is to make those maps of the cosmic web, for example, those clusters and filamentary structures going between them. Neutrinos also affect the pattern, the statistics of the patterns of those lumps and bumps in the cosmic microwave background. So actually the cosmic microwave background is one of the best measures we have of the neutrino mass, which we talked about earlier is really hard to measure, and we still don't know exactly how light they are. So it has implications for a lot of different areas of science.
Just a warning, we probably only have time for 1 or 2 more questions, but I'll try to get as many people as we can. And Dr. Lowitz said she will be at the coffee hour afterward as well. So.
At Amundsen-Scott, is the 300 Club still active there?
So it is. So the 300 Club, which you can it has its own Wikipedia page if you want more information. So because we get down to minus 100 Fahrenheit in the winter, and because we have a sauna that gets up to plus 200 Fahrenheit whenever you want it to, that means that you have the opportunity to do a 300-degree temperature swing, should you desire to do so. So the idea with 300 Club is that you sit in the sauna at 200 degrees until you want to die, and then you run outside around the pole marker and back in. And if it's true 300 club, you must do this wearing only boots. So that is still a thing.
My question is a little bit more on the practical side of this. How much do one of these telescopes cost, and how much of it is actually supported by the United States versus other countries, and how many researchers across the country and globe are actually support their research based on the data coming out of one of these telescopes?
So again, I'm going to answer for South Pole Telescope because that's the one I work on, and so I know more stuff about how our collaboration works. So our collaboration, the edges of it are a little bit fuzzy because there are people who spend, 30% of their time working with our data and the rest of their time working on other things. But roughly speaking, our papers that include sort of everybody are sort of 70 to 80 people. Though there are certainly other people who touch our data or who work on data that's informed by our data, or it does get broader than that. But that's kind of the rough size of the collaboration. Not all of those people are being paid by us, so many of them are professors who are paid by their universities primarily and not by the grant. Many of them are on fellowships that are supported externally and not by a grant directly. So I have no idea what fraction of those people are paid by the grant. I am paid by the grant completely. And many of the postdocs in particular are. It's more common to have fellowships as a graduate student. The cost of the telescope, so for to build SPT and run it for the first 3 years, which was the duration of the original camera, I believe was $20 million. So a whole lot cheaper than going to space, that's for sure.
All right, I'm going to say this is our last question.
Hi, as a postdoc who looks at atmospheric observations, I have a couple insignificant nerdy questions about, in particular, just details on some of the measurements. One, do atmospheric inversions ever impact your measurements? And
we are not, so atmospheric inversion, for those who aren't climatology nerds, is, so typically if you go up in altitude, it gets colder. But the South Pole is one of the places that's very unusual in that it is normally the other way around. It's colder closer to the ground and warmer if you go up, at least up to a certain point. So that is the sort of way that things normally are at the South Pole, and that's sort of interesting for a lot of reasons. But for us, it doesn't affect us because we're not looking very close to the ground, in particular because the atmosphere is very thick close to the ground. If you look at very low elevation, you're sort of at the angle that makes you look through the largest amount of air, and that's disadvantageous for us because of atmospheric refraction and also because there is some water vapor in the atmosphere. So we don't observe any lower than about 30 degrees of elevation where the atmosphere is a lot thinner, and we're just not that affected by the ambient temperature.
And two, how long does it take to get an adequate sample out of the microwave radiometers?
So, I mean, it depends on what you mean by adequate sample. We can see point sources instantaneously. That's how we check if we've put a new camera in, whether we did it right and can see anything. So we scan across an object called RCW38, which is an H1 star-forming region. And we can just immediately, instantaneously see a blip in the detectors. In order to make a map where you can see the temperature fluctuations in the cosmic microwave background, we have to, we raster across a big patch of sky. So the telescope goes over and back up, over and back up, over and back up. And we just have to do that once to make a picture where we can see the temperature fluctuations, those lumps and bumps that I showed you in that oval picture. So one scan of that patch takes a couple hours, just seeing each spot once. To see B modes, which are that imprint from inflation that we're all looking for, that takes, if we're lucky, maybe we'll see it after scanning for 4 or 5 years continuously all of the time. Maybe not, because we don't know how strong that pattern is. We have theory predictions tell us a ballpark of what strength it could be, but that's still sort of an order of magnitude. of range that it could be in. And so if it's at the top end of that range, we'll probably see it. If it's at the bottom of that range, it may not be possible to detect it with any telescope you could build, even if it were there.
Thank you so much, Dr. Lowitz.
Thank you.